Okay. Um, so continuing on where I left off last time. Now, the last time we defined a PDE, of course, we referred to a function u that satisfies a PDE as a solution, but there's actually different types of solutions. So, solution u of a PDE that is of order k. So in other words, there are derivatives of up to and including order k in the PDE is either a classical solution, also known as a strong solution, if u belongs to the space called CK, and again, it's not c to the kth power. So this is the space of functions that are k times continuously differentiable. So for instance, the absolute value function is only in C0. It is continuous. It does not have a continuous derivative. So if all the derivatives that are required just to substitute into a PDE exist and are continuous, then it's a classical solution. By contrast with the other term, strong solution, it is a weak solution otherwise. Weak solutions often come up in finite element methods, where a second order PDE is rewritten as an integral equation involving only first derivatives. So only the first derivative has to exist for it to be a solution. And in some cases, for weakened, so a lot of PDEs have strong and weak forms. And having a weak form is nice because then your solution doesn't have to satisfy quite as many conditions. That could be nice for numerical solution. So to give some examples of both strong and weak solutions, so Laplace equation, Laplacian of u equals 0. And we'll talk more about this equation later, but any solution to Laplace's equation is a classical solution. In fact, we can make a stronger statement, because being a classical solution in this case would only require that u is twice continuously differentiable, that it belong to C2. But in fact, it can be shown that u is in C infinity. It has continuous derivatives of all orders. Okay. Another example, the one-way wave equation. And gave an example last time, ut plus ux is 0. So this is a advection equation where the solution is just the initial data propagated to the right. So let's suppose that the initial data is C1, so it has a continuous first derivative. So in that case, whatever solution we get, u of xt, which in this case we know what it is, I mentioned it last time, it's u naught of x minus t, is classical. In other words, it belongs to C1, just because you're taking a shift of a C1 function that is also C1. And because the PDE only has first derivatives in it, being C1 is enough to have a classical solution. I have to remember to keep an eye on this computer because it keeps stopping the recording. More examples for weak solutions. Suppose I have this second order PDE. So if I were to carry out the product rule, I would get B times UXX plus B prime UX is equal to 0. So this is the second order. And I'll impose the boundary conditions. U1 equals 1. So then I'm going to define this coefficient to be piecewise constant. So, I thought I'd welcome Elise to the class with memories of her honors thesis work. Well, I mean, you've been working on this problem too. Okay, so it turns out you can figure out the solution to this by integration, and what you get since the coefficient is piecewise defined, the solution is too, and you get 4/3 x for x less than 1/2, 2/3 x plus 1/3 for x greater or equal to 1/2. Now, what ends up happening is the solution, if you were to plug in, because each of these by themselves are continuous, if you plug in x equal to 1/2 for both, you get 2/3 here, and you get 1/3 plus 1/3 is also 2/3. So it is continuous. It's at least C. But let's look at a derivative. U prime of x is equal to, will just be 2/3, 4/3 in this case. And then it's equal to only 2/3 in this case. So I'm checking out something else here. So it's C0, but it is not in C1. So we actually needed it to be C2. Now, the second derivative is 0 throughout, but this constituting the first derivative kills it. So, and it kills any chance of it being a classical solution. It is only a weak solution. Okay. Any questions so far about this weak solution? One more example that I can do this for. This equation came up last time, one of the examples. Berger's equation. Ut plus UUX is equal to 0. And let's assume that the initial data is C infinity, so infinitely smooth. This is only a first order equation, so you're going to think, well, if the initial data is in C1, surely the solution will be in C1. But this is a linear, actually quasi-linear equation. Um, uh, but the trouble is, the solution becomes discontinuous at t is equal to 2. And no, not something I expected to see just by looking at the equation. That's something that would have to be worked out at length to show that it actually happens at t equals 2. So therefore, u is not even in C0. So this is definitely a weak solution. Okay. All right. I know I always set myself up for embarrassment by going off script, but sometimes I just can't help myself. So this solution, this equation can be described implicitly. So u of xt is equal to, well, I'll first describe it. So u of x0 is equal to some function u naught of x. So then it'd be u naught of x minus u times t. So u, unfortunately, appears on both sides of the equation. So what happened is, for instance, du dx would be equal to u naught prime x minus ut times the derivative of what's inside, which is 1 minus ux. And therefore, what you can do is I can rearrange and solve for ux. So ux is equal to u naught prime over 1 plus u naught prime. Okay. Whereas ut would be u naught prime again, but then I differentiate this with respect to t. So I differentiate what's inside. So to differentiate the x, I'm not going to get anything. But what I'm going to get is minus ut times t minus plain old u. So then what I can do is solve for ut. Oh, sorry, forgot. Yeah, forgot a t there. See, what did I tell you? Set myself up for embarrassment by doing things off script. Okay, so, all right, so 1 plus t u naught prime is equal to minus u naught prime. So then I can solve for ut is equal to minus u naught prime of x minus ut over 1 plus t u naught prime. And what we can see is ut plus ux is equal to 0, because the difference between this and this is only the factor of minus u. Because Burger's equation says that ut is equal to minus ux. And here's the only difference between them. So, all right, at least I have the solution right. But the reason why I did this in the first place was try to shed some light on the nature of the discontinuity. That what ends up happening is the solution at some point no longer has a unique value. And I was hoping that something would jump out like, oh yeah, it happens at t equals 2. But nothing like that is jumping out here. And dealing with method of characteristics is something that we'll be dealing with these kind of equations more later on. Let's see. Okay, well, I'm going to stop at charade, but because depending on the initial data, certainly you can see how, because what ends up happening from computing solutions of this before, you end up having a situation where the slope gets steeper and steeper, and at some point it just becomes infinite. But in what way that happens would certainly depend on the initial data. And I have to check if where I got the example for this from, if some initial data was actually specified, and I just forgot to include it. So, okay. So I'll check on that later. But at least it's an interesting exercise in chain rule. So nothing else. Okay. So the point is, how many solutions your derivative has. Continuous derivatives determines whether it is a classical or a weak solution. Okay. Now, this next bit I'm going to cover is going to set you up to be able to do the first homework problem, and then you'll be done with 10% of a course. So Fourier methods for linear IVP, initial value problems. So we'll see IVP for initial, BVP for boundary value problems, and even IBVP for initial boundary value problems. Okay. So a few initial value problems of interest. So ut is equal to ux, that is a linear advection equation. What we saw close relative of ut equals minus ux a little while ago. We have ut equals uxx, which is the what equation? Yeah, equation. And then we have ut equals uxxx, that is called Airy's equation. And we even have ut equals uxxxx, that is the beam equation. I haven't seen an equation of like actual applications of order greater than 4 yet. Okay. Now, depending on the domain of a problem of a PDE, use different Fourier transform. So, if your domain, and using omega to refer to, I started this notation last time, to refer to the domain of a PDE. So, if it's a whole real line, then you can use what is called the continuous Fourier transform. U of xt is as integral of, yeah, this is the actual Fourier transform, u hat of omega t, where u hat is 1 over 2 pi, also an integral from minus infinity to infinity, e to the minus I omega x dx. Okay. Depending on what books you use, or what sources, the Fourier transform may be written differently, like a different scaling constant, or maybe like a 2 pi here and here, and no scaling constant, but it's different forms. But
isn't that if you're using like? Okay, never mind.
Okay. And these are nice because it allows you to reduce the PDE to an ODE. So instead of having a PDE in x and t both, it becomes algebraic in equation in omega, and therefore an ODE in t. Now, on the other hand, if we're on a finite interval, so let's say minus pi to pi, then we use a Fourier series. That's a discrete analog of the continuous Fourier transform. So you can see is the sum where you have these Fourier coefficients, e to the I kx, where k is an integer indicating the frequency. And the Fourier the coefficients of a Fourier series are obtained in terms of these integrals. And you can see the analog between these Fourier coefficients and these. So it's always integral over the appropriate domain, e to the minus I times frequency times x, and the function that you're transforming.
And the notes, it has a square bracket of the negative pi, is that a typo?
Oh. This is a typo. Well, there's actually been different conventions about this. Following the author of the MIT notes for finite interval, he tends to define these for periodic lists to include this left-hand point, but not the right one. I tend to define the PDE only on the interior because you're imposing conditions on the boundary. But so from now I'm following what he used.
But it doesn't really matter.
In terms of solution process, no.
Okay.
Besides, you can always have a situation where the boundary conditions are like there's an incompatibility.
And so then you would just use both of your parentheses.
Right. Yeah. Okay. So let's work with this case of on a bounded domain where we're solving an equation of this form where we have u dt is equal to some derivative of x of whatever order. Here I have orders 1, 2, 3, and 4. So we're just going to have a PDE that accounts for all 4 of these cases. Because the solution process will be the same. Getting some glare on the video here. Well, this recording picked a good time to drop out. All right, so PDE we're going to look at is UdT minus f derivative of u with respect to x is equal to 0.
So I have a question.
Yeah.
I mean, if you're writing it in the way that you're writing it on the right board,
Yeah.
which I like so much more, I mean, it would just be like ut and then like minus u x to the end.
I could, yeah. But
Could you?
yeah.
Like, I mean, will you?
Like right now?
Yeah, like, could you? Yeah. I like that notation a lot more.
Okay.
Yeah, so I know it means the same thing. It helps.
Okay. Whatever you need. Yeah. All right. So now what I can do is if I substitute the Fourier series representation in for u, then I have the sum. And I have, again, I'm trying to now we have a ordinary derivative of the Fourier coefficients.
Yes, thank you.
Okay. And then here we're taking the nth derivative of the Fourier series with respect to x, but the only dependence on x is the e to the ikx. Well, when we take a derivative of that with respect to x, this is going to multiply by ik. And we're taking the nth derivative, so it's to the nth power. So now we have that. So this all happened by substituting the Fourier series in the upper board into the PDE and then just carrying out the differentiation. So differentiating with respect to t, we just differentiate the Fourier coefficients. Differentiating with respect to x, we only differentiate the exponential, which introduces this factor here. So any questions on how we got this one?
Hold on, sorry.
Okay.
Because I was trying to do homework, so I had questions on this stuff. Like, give me a second.
Okay.
She just differentiated the exponential. Oh, okay, yeah, cool.
Okay.
Sorry.
All right. Now, these functions, e to the ikx, are linearly independent. Well, in fact, they're orthogonal. But right now, we need is the fact that they're linearly dependent. And what that means is, when you have a linear combination of linearly independent vectors or functions equal to 0, that means that the only way that can happen because of the linear dependence, that's the definition of them, all these coefficients must be equal to 0. So now we have the Fourier coefficients must satisfy this ODE, and but this is very easy to solve. So we just have whatever the initial value is, which would come from the initial data, times e to the ik to the n times t. And actually, I give a formula for the initial value from the integral over there. So e to the minus ikx times your initial data, whatever that is. Okay. So now we can just write down a solution as a Fourier series. We just have 0 e to the ikx, e to the ik to the n t. So now we have a formula for a solution for whatever n. I want to go back to to these four cases where n is equal to 1, 2, 3, or 4. Although, you know what? I think I might have goofed. The 4, 4 to 1 is actually not the beam equation. The beam equation has a second derivative in time, so I'll have to erase that. It's still a case we're going to look at, but I just can't call it the beam equation. Oops. Okay. All right. So if we go ahead and look at the cases n equal 1, 2, 3, 4, we get some interesting behavior. Insight into behavior solution from the Fourier series representation. Wait, that was weird. Hold on. Okay, I'll have to keep this in mind later when I upload this enhanced, because right now, yeah, maybe it's because I shut off my glare. Okay, at first it's like I can't even see the writing on the board on my screen. But when I upload, I'll enhance so that it shows up. Yeah, because like I angle my laptop a little differently, and all of a sudden, like the lighting changed, and you can see things much better. Okay. So for this case, if we take a look at, see what the solution looks like. So n equals 1. So I have, I'm going to be lazy here. It's understood in all cases k goes from minus infinity to infinity. I'm not going to keep writing it. And we have e to the I kx, e to the I kt. But I can write that as e to the I k x plus t. So what happens is, well, what kind of graph transformation is this? We know what this is? Yeah, shift to the left by t units. So that's all you have going on. And there's no change in the amplitude whatsoever. There's just this shifting. So we just have pure advection. What about k equals 2? E to the I kx, and then we have e to the minus k squared t, because I squared is equal to minus 1. So what happens is we get exponential decay. And the higher frequency of the waves, the larger value of k, the more rapid the decay is. And that has a big effect because it's k squared. So that's why solutions of a heat equation, even if initial data is not smooth, the solution becomes smooth very rapidly. Because any high frequency oscillations are quickly go to 0. Okay. What about n equal 3? So I have e to the I kx, and then e to the minus I k cubed t. So I can write that as e to the I k, and then I have x minus k squared t. Okay, I have to keep a closer eye on this thing evidently. So when I'm just watching what was preserved, I'd gotten as far as writing this. So, okay, so very quick summary for anyone. Well, I guess only one person has to watch this. Okay, so what we have is waves traveling at, they don't lose their amplitude. Their amplitude is just the absolute value of this initial value. But they're all shifting at different speeds, k squared. That's called dispersion because the waves are separating from one another. So we have advection, diffusion, dispersion. So here we have just straight propagation. Everything shifts together. Here diffusion, where waves decay off. Here we're separating. here we have, in this case, I to the fourth is 1. So we have just k to the fourth t. So who can tell me what's happening to the waves in this case, in contrast to the other cases?
Opposite of diffusion.
It is, yeah.
Yeah, but I mean, I don't know.
Well, it's exponential growth.
I don't know if you call it like.
The amplitude is going to grow exponentially. Therefore, this is unstable. This is actually an ill-posed problem, like the backward heat equation for a similar reason, exponential growth in the waves that we get. So a slight change in initial data would cause an exponentially large change in the solution. So this is not a viable PDE to solve. If it was ut equal to minus uxxxx, that would be okay. Okay.
So if it was minus, then it was decaying, and it was stable.
Yes. Okay. So, for more general linear PDEs, particularly those with constant coefficients, if we assume solution has this form, u of xt is equal to e to the minus I omega t e to the I k x. So what you do is you substitute this into the PDE and figure out what is omega. So omega is unknown. Or actually, sorry, in the notes it was just written as a plain old W, not omega. So you solve for W in terms of K. So it's going to depend on K. And this is called a dispersion relation. So what happens is e to the I kx, so this wave that's part of your initial data is transformed by e to the minus I w of k t. So each PDE is going to produce its own dispersion relation, and depending on what your dispersion relation is, that tells you what kind of phenomenon you get. Do you get actual dispersion, or do you get diffusion or advection or instability? Okay. So what I can do now is show you. So to give an example from one of the PDEs that we just saw, like ut is equal to ux. So if I assume that u has this form, so I get minus I w e to the minus I w t e to the I k x, that's ut, is equal to ux, which gives e to the minus I w t e to the I k x times I k. So then a whole bunch of things cancel out. All the exponential cancel out. The i's cancel out, and your dispersion relation is w is equal to w is equal to minus k. So that's the dispersion relation in the case of n equals 1. Whereas for diffusion, if you go through the same process, you get w is equal to minus. Okay, let's see how long it can last. Okay, so these are, so you get an idea what dispersion relations would be in cases, or we can match this against what we get in the solution here. The part is multiplying e to the ikx to see what the dispersion relation is. But what I'm going to do is write down some examples of various PDE and what their dispersion relations are and what they mean for how the solution behaves. So some examples, we have the wave equation. So even with second order PDEs, you get dispersion relations. So what we get in this case is W is equal to plus or minus CK. So you can convince yourself of that by substituting that form of solution I wrote earlier into the PDE and carrying out the differentiation in respect to x and t, and then simplifying as much as you can. And when you get it in this case, you get a quadratic, you get a relation between W squared and K squared. That's when you take a square root, and that's why you get the plus or minus. What kind of behavior that you get is called conservative. Just because you have the situation e to the plus or minus I c k t, so that is your W there, and magnitude is equal to 1. So the waves maintain their amplitude for all time. Because what I wrote over there, we have the transformation is e to the minus I w t, and that determines where you see if you get growth or decay or magnitude staying the same. Heat equation, this is a wave equation. Heat equation, more generally, is ut is duxx, there's some coefficient d. So your dispersion relation is minus I dk squared. So this is called dissipative. Reason being e to the minus dk squared t in magnitude goes to 0 as t increases. We also have convection diffusion. So that's ut is equal to, you have an advection term or convection term, cux. So first derivative gives you convection, and then we have the diffusion term like in the heat equation. So your dispersion relation is minus ck minus idk squared. So it's kind of like a combination of a previous two dispersion relations. That one turns out to also be dissipative. Because the magnitude of e to the minus I minus ck minus idk squared t, which is the same as e to the ick minus dk squared t. This part is going to stay the same in magnitude, but this is going to cause decay to 0. So it's a different flavor of dissipation than the regular heat equation, but it's still dissipation nonetheless. So waves of higher frequency going to 0 rapidly. The Schrodinger equation. Rather strange one. IUT is equal to UXX. So it's a heat equation with an I in front of a time derivative, which leads to very different behavior. So your dispersion relation is W is equal to minus K squared. So you can separate all this. So the behavior in that case is dispersive. Because you have e to the ik squared t is equal to 1 in magnitude, but the waves are traveling at different speeds, like with Airy's equation. So that's why you get dispersion in that case. And in fact, Airy's equation, we have ut is equal to uxxx. So w turns out to be k cubed. So that turns out to be dispersive also, because the magnitude of e to the I, or minus I k cubed t, is equal to 1. So the way this works is, you substitute that form I wrote over there, e to the minus iwt e to the ikx, substitute it into the PDE. Solve for w, that's your dispersion relation, after you carry out the differentiation. Then you look at, in all cases, this is magnitude of e to the minus I w t, and you ask yourself, what happens to the magnitude of that? Does it go to 0 as t increases? Does it remain equal to 1? What happens to it? Does it grow? In which case it's unstable. So for whatever PDE you have, this is what you look at. Now, all of these PDEs that we're looking at are constant coefficient. Not sure if this would be useful for variable coefficients. Probably only get like an approximate dispersion relation, because that dependence on x complicates matters. But from a constant coefficient form, you can still get ideas of what the general behavior of a solution is for constant coefficient or variable coefficient cases. It's if the coefficients change sign on you, then you might have a problem. That would drastically affect behavior that we see here. Okay, so this is a good spot for a break. So. Okay, one more questions.
One more question.
I'm surprised you have them already. But
I always start off this semester
because only now can you really touch the first problem. And when. Okay. So. Okay.
Okay. So you went over a problem. Like, okay, I can essentially get to the point where I have the series, and then I set the coefficients equal to 0.
Yeah.
But
how to solve the ODE?
Yeah. How do I solve the ODE again?
Rely on your undergrad DE course knowledge.
Okay.
Yeah.
So this is just DE course, regular, whatever stuff.
Yeah, because since you have a general second order linear ODE of constant coefficients, you find a characteristic equation.
Oh, characteristic equation. Okay.
Yeah.
Cool. All right.
Yeah.
Yes.
Yeah. So yes, number 1 is the only problem that's safe to touch right now.
Characteristic equation, all that kind of stuff. But it's just, same thing.
Yeah.
I talked to Emily, I was like, she don't care. She wasn't even listening.
You're recording. Although probably didn't hear you because you're back in the back of the room, but well, I'm sure she won't watch. Okay. Okay. Anyhow.
Okay, first of all, maybe Abdullah will watch this, but it does crack me up that that's all he says now. Anyhow. Yeah. Goodbye from you.
Oh God, I created a monster. Okay. Let's see. Next section. Now we'll get some time-independent PDEs. Laplace's equation, Poisson equation, which are extremely similar, just that one has a 0 right-hand side and the other doesn't. So Poisson's equation, we have minus Laplacian mu is equal to f. The minus is not absolutely essential, but the convention is often followed so that the differential operator on the left side is positive definite. In some domain omega. So here's our domain. And I'm going to divide the boundary into two segments. Whoops, that's omega. I meant gamma for boundary. So the boundary of omega is the union of two portions, gamma 1 and gamma 2. So for instance, this could be gamma 1, and this might be gamma 2. All right. And I'm going to impose different boundary conditions on these different pieces of boundary. So, yes. After the previous one suffered a hard drive crash. So, I'll take the trade, but still. Now, not sure how much was missed, but n is the outward unit normal vector pointing out. So that's a convention that we follow. And using a concept of directional derivative for multivariable calculus, normal derivative can be defined to be the gradient of u dot product with the normal vector. Okay. Now, if f, the right-hand side, is equal to 0, then this becomes Laplace's equation. And we could have the same boundary conditions if we want. And in that case, Laplace's equation, the solution u is said to be a harmonic function. That's just for Laplace's equation, not Poisson's equation. Okay. Now, one situation in which Poisson's equation or Laplace's equation can arise from a time-dependent problem is if we consider a heat equation with an external source. So you have some heat source, and that would be ut minus the Laplacian is equal to f. But then, let t go to infinity. And what happens is, due to the smoothness of the solution, we have u dt is going to 0. So the solution converges to a steady state. And if we just set ut equal to 0, then what are we left with? We're left with exactly Poisson's equation. So the steady state solution of a heat equation with a source term satisfies Poisson's equation. If there's no source, then it satisfies Laplace's equation. Okay. All right. So what I need to do now is obtain what is called the fundamental solution of Laplace's equation, where that is actually used to obtain like a general solution to Laplace's equation with whatever boundary data you have. So a fundamental solution is in free space so no boundary. So basically, we're in all of R n. Okay. So that's what free space means. Okay. Now, we're going to assume that a solution, u of x, is radially symmetric. So R is your radial variable. So you think of it being like your R from polar coordinates or your rho from spherical coordinates. but it's generalized to n dimensions. So this would be also written as the norm of x from linear algebra world to norm. It's square to sum of squares. Okay. And it satisfies this on all of Rn except for the origin. We're going to have a singularity. And that's what we're actually going to see in the solution we end up getting. Okay. So, I want to transform Laplace's equation into an equation involving only derivatives with respect to r. So I need to be able to express derivatives of r with respect to the x's. So with this definition of r, partial derivative with respect to xi is going to be, so 1/2, and then this to the minus 1/2 times the derivative of what's inside with respect to xi. That's just going to be 2xi. All of our terms have a derivative of 0. So the 2's cancel out, and I'm left with xi over this square root. But that just simplifies to xi over r. So now I want to take the second derivative too. So second derivative. So I can take a derivative of this with respect to xi, and that's just going to give me the, I need a quotient rule. So that's going to be r times the derivative of xi, which is 1, minus xi times the derivative of r, but that is just xi over r again, all over r squared. So now I can simplify that, and I get 1 over r minus xi squared over r squared. So, now if I assume that u has this form, then a partial derivative of u with respect to x is going to be v prime of r, partial of r with respect to xi, but I have that. And then, but I want the second derivatives, because that's what makes up the Laplacian. So using a product rule on this, I'm going to get v double prime of r, xi over r. Let's see. Well, hold on. I need to write an intermediate step here. Differentiating this, I'm taking derivative with respect to xi, not r. And then I still have this out here. Now when I differentiate this with respect to xi, that's the same as differentiating with respect to r times the derivative of r with respect to xi. But that I have up here. So, sorry, I've been focusing so much on this one step that what I've written on the board is technically incorrect. So, I have derivative of that times that plus this times the derivative of that. Okay. So this term is just going to keep traveling with me. dr dxi is xi over r. And I have another one here, so that's going to be squared. So I'm going to have derivative of this, that's just v double prime of r, times dr dxi, which is this, and then that again. So I have xi squared over r squared. Now, derivative of xi over r, I already did that down here. So really it's just the second derivative of r with respect to xi, and for that we have this formula here. So we have v prime of r, 1 over r, minus xi squared over r squared. Okay. Hold on. It is a correct derivative, but I just want to see a presentation to humor me. There's certain things that worked out sooner than I. What?
When you took the second derivative and the numerator, the second term, you have xi over r.
Yeah.
And then when you separated the two fractions, wouldn't that r combine with the r squared in the denominator? And wouldn't it be 1 over r and then minus xi squared over r cubed?
Okay, I need to know where you're pointing exactly.
When you yeah, there. The second
right.
term. Yeah, that when you broke it up into two fractions.
Okay.
So on the other side, the equal sign.
Okay. I need to think. Sorry, not my day. Okay. Ignore that. It's not wrong, but this is how it should be presented. Okay. The best thing to do is actually not fill in those derivatives just yet, because it's really the second derivative after, because Laplacian only contains second derivatives. Okay, so now we're differentiating. So from product rule, okay. Now, this would be derivative with respect to r times dr dxi by chain rule. Okay. Now, by waiting as long as possible to fill these in, you take advantage of a formula that I've worked out over here.
So this is rewriting.
Yes. Okay. I know I'm being anal, but I the whole time I was running it, it's like, I hate this presentation. And I just wanted to banish it. So this is a presentation I'm okay with. So please ignore the other, even though it's not incorrect. So v double prime of r squared. But now we can fill in what that is, and that's just xi squared over r squared. And then here we have v prime of r. And this one was worked out earlier, so 1 over r minus xi squared over r cubed. Not sure what I was thinking when I looked at my paper earlier, which clearly said r cubed, but I wrote r squared. Okay. That's it? Okay. Because I'm going to keep going, so. Now, this is one partial derivative with respect to xi twice, but on the Laplacian. So that would be the sum of all of these partial derivatives. So that's going to be v double prime times so all of those are added up. But the thing is, well, I'll write the rest of this first. Then I have v prime of r that I factor out, and then I have 1 over r n times, because I'm adding up n times, so that would be n over r minus v prime of r. I'm going to factor out the 1 over r cubed sum xi squared. And in fact, here too, r squared doesn't depend on I. I'm going to pull it out. Okay. But what's the sum of all the xi's squared? Almost. R squared. Yeah. So this is r squared. This also r squared. So these cancel, and this gets reduced to 1 over r. So what we get is v double prime of r plus v prime of r n minus 1 over r. So that's what the Laplacian looks like in these in the radial variable. So if you assume your solution is radially symmetric. So what's interesting here is the derivative of Laplacian depends on the dimension of the space that you're in, which means it's going to affect the form of the solution. So now if we look at, if we set this equal to 0, so Laplacian of u is 0, so I have v double prime of r plus n minus 1 over r v prime of r is equal to 0. This is it's a second order equation in v, but it's a first order separable linear equation in v prime. So that says that v prime is e to the integral of this minus this coefficient well, times a constant, which I'll just call b. And we have here e to the 1 minus n natural log of r. But how does that simplify? Something my DE students last semester messed up routinely. Almost. So
Don't you just pull so 1 minus n is like a constant, you just pull it out front and then that's just
Wait, what?
Yeah, and R, isn't it R?
The key is what do you do with the exponent before you do anything else?
So you said
Are you saying
the
like-
exponent
Oh, e to the
two
first over e to the n.
Uh,
And then,
no, I can't quite do that.
Stick it out in front of the
Oh, wait.
front.
oh, the
R to the R to the 1 minus n.
exponent to
Yeah,
the
R to the 1
exponent.
minus n.
Yeah, you can put it somewhere, but yeah.
R to the 1.
E to the ln r to the 1 minus n. So it's b r to the 1 minus n.
ah.
Now, but that's v prime. We actually want v. And let me just make sure I'm capturing all this. Yep. Okay. So to get v, now we can go ahead and integrate this. But how that works out depends on the value of n. So v of r is equal to, so in the case of n equals 1, all we have here is a constant. So we have a linear function for v. If n is equal to 2, we have b times r to the minus 1. So that's b integrated natural log of r plus a constant. And if n is greater than 2, then you're using the power rule. So we have so that would be b, so some constant over r to the n minus 2 plus c. Now it's not going to be exact, it's not exactly this b. There's a constant factor. Without any further interruptions. So for any b and c, we have a solution of Laplace's equation. But there are certain solutions that are of particular interest because really we want to use this fundamental solution to be able to solve Laplace's equation for various boundary conditions. So I'm going to impose an additional condition. So if we require that the integral over the whole space, well, we have to exclude the origin because that presents some problems, of, well, actually, no, I have to include everything. Because the thing is, these solutions, except for n equals 1, the other two solutions are not defined at the origin. But if we require that so it's the general volume element over Rn. Yeah, that's what I want. So the integral over the whole space, even though Laplacian is 0 on the entire space except for the origin, we don't know what's happening at the origin, but by requiring that this be satisfied, then the fundamental solution of Laplace's equation is these solutions with certain choices for the constants. So for n equals 1, we have, well, instead, in place of r, I'll write the magnitude of x. But that case, actually, one dimension that's just absolute value. For n equals 2, I have minus 1 over 2 pi natural log of the magnitude of x. And this is for, and finally for n greater than or equal to 2, or n greater than or equal to 3, rather, we have 1 over n minus 2 alpha of n, which I'll define in a moment, times magnitude of x to the n minus 2. where alpha of n is equal to the volume of the unit sphere or unit ball in Rn. So for example, if we were in 3 dimensions, it would be the volume of a unit sphere. 4/3 pi, and so on. Now, these constants are chosen so that the Laplacian is equal to this function, the Dirac delta function. Now, the Dirac delta function is a very odd duck indeed, because it satisfies these strange properties. It's equal to 0 for x non-zero. However, the integral over the whole space is equal to 1. So you could try defining it something as like maybe infinitely large or something at the origin. But the thing is, the delta function is technically not a function. It's what's called a distribution. And I remember in my first year at Stanford, we had this one awful professor who I shall not name teaching a course like this, and he was trying to explain what distributions are. He actually resorted to the cat in the hat, which all of us found rather strange. That you can't define a distribution by what it is, but rather what it does. And he's relating this to Boom from Cat in the Hat. So I don't think it really helped us any to understand it. So a distribution is not a function in the usual sense, but it's helpful for developing formulas for solving PDE, certainly, by requiring fundamental solutions to satisfy the PDE that you're solving set equal to the delta function as a source term. And so I can show you how this can be used to solve Laplace's equation, or actually Poisson's equation in general. All right. I won't get through to the end of this section, but pretty close. Okay. So then the solution of Poisson's equation, free space solution. So again, no boundary data, is given by integral over Rn, and it's a convolution of your fundamental solution with your right-hand side. Now, to show you why this works, I can take minus Laplacian of both sides. Now, here I'm taking Laplacian in respect to x, and we're still taking Laplacian in respect to x on the right side. So that would be, so I can move Laplacian inside the integral, but I'm going to use this subscript here, x, to indicate that I'm taking Laplacian in respect to x, not y. And what I end up getting is, well, this is the delta function. Delta of x minus y, f of y, dy. And what this delta function does happens to select the value of this function at the point where this argument is equal to 0. In other words, when y is equal to x. So this is how the Dirac delta function works. We get f of x. which is exactly what we want for Poisson's equation. So phi is what's referred to as the Green's function for Poisson's equation. All right. Now, yeah, I don't want to rush for the rest of it, so I'm going to stop here. But we'll pick up with harmonic functions tomorrow. It's weird to teach the same class every single day. Okay.